Welcome to chapter 5 that will deal with redox chemistry. We will first shortly present the redox theory, what is a redox reaction, the oxidation state, and how to balance redox equation. I will show you a method that I think is it's a very good one to be sure that you're balancing any redox equation the right way. Then we will use those notions into defining element cycling. Not spend too much time, of course, but just show how to use redox chemistry and also acid-base, chapter 4, to understand element cycling, and also life. Because life can be seen and nothing else, and organism, like us, like bacteria, like any other organism, doing redox chemistry in order to get energy to perform metabolism. So first of all, let's go back to our fundamentals and our periodic tables. We have seen that the periodic tables are organized in groups 1, 2, 3, 4, 5, 6, 7, and 8. And that you have trend in the periodic table, and one important trend was electronegativity. The affinity, if you want, within the molecules, the affinity of an element to attract electron. An example, if I'm taking an example we've seen many times in this class, the salt NaCl. We know that sodium is from group 1, is having 1 valence electron, and chlorine is group 7, is having 7 valence electron. So we have seen that sodium has no problem to give electron away because you want to have this full octet, and chlorine want to grab one more electron, is way more electronegative, and want to take this electron. So when we have NaCl structure, the electron are spending, the share electron are spending all the time surrounding the chlorine. Chlorine will hug this electron and rub it from the sodium. So if you want to have a virtual charge of the sodium and chlorine within this molecule, chlorine will be charged positive. Sodium will be a positive charge, and chlorine will be a negative charge because it will rub this electron from the sodium. And this is what we call the ionic bond. If we're taking now an example, a different example of a non-ionic bonds, let's take very popular, we spend a fair amount of time dealing with H2O, water, when we're dealing with acid-base. And if you remember, again, now we're familiar with that, you have this structure, this Lewis structure here, and as you know, we have the negatively charged zone here and the positively charged zone here, because the electron that is shared between hydrogen and oxygen will spend more time around the oxygen than the hydrogen, because the oxygen is way more electronegative than the hydrogen. But this is not an ionic bond, and this will give you a minus charge here and a positive charge here. This is the real way of representing a molecule. If you want to simplify that, if you want an idea to simplify this view, a chemist came out with a simplification, if you want, for this type of setup, for those type of covalent bond. And to do that, we will see this molecule as it would be an ionic bond. This is not an ionic bond, it's a covalent bond. If the electron will spend all the time around the oxygen. The charge in this case, the oxygen will take the 2 electrons from the 2 hydrogen, and this electron will spend all the time around the oxygen. So the charge of this oxygen will be, in this case, 2 minus, and the hydrogen will be positive because they will give the electron to the oxygen. This is by convention we writing the charge of this element within a molecules with the sign after the number. We're not writing -2, we're writing 2 minus. So this is what we define as a oxidation state, or number if you want. This oxidation state or number is an artificial way of estimating the charge of an element, an atom, within a molecule. And this is based on the electronegativity, the ability or the affinity of an element to grab an electron. So in this case, we can link that to redox chemistry. When redox stands for reduction oxidation, there's always, when you have an oxidation, you will always have a reduction. And you know, I'm sure you know that a reduction, an element is reduced when it's gaining electron and is oxidized when it's losing electron. In this case, hydrogen here is oxidized because, let's use a different color here to see that in this case the electrons are moving from the hydrogen toward the oxygen. Okay, so in this case the H, let's use a better color here, the H are oxidized because they're losing electron to the oxygen, and the oxygen is reduced because it's gaining electron. We can say that the reduced term is because this number here is going to be smaller, it's going to be negative, if you want to have some kind of idea to link that to a logical way of seeing things. Let's go back to our periodic table and see the different groups. Oxidation state is closely related to the group, to the valence electron, and the electronegativity in the molecule, how specific elements, atom, is willing to grab or to give electron. If you take group 1, for example, they have one valence electron and they are willing to give it away. So often they're giving away this electron in a molecule. Again, this is a simplification. They're sharing electron, but if you want to simplify and have a positive side and a negative side, those elements for group 1 will give this electron away and will have an oxidation state of 1 plus. The group 2 will have more likely to have 2 plus. The famous ones are calcium 2 plus and Mg 2 plus. When they are under the ionic form, they're actually losing those 2 valence electrons and giving those 2 electrons away. They're getting oxidized. Opposite side of the spectrum, if we take group 7 here, fluorine, chlorine, bromide, they will more likely to accept 1 electron, to grab electron in a molecule. That means they will have likely to have -1. For group 6, oxygen, sulfur, will more likely to have 2 minus. Of course, there will be exception depending on the complexity of the molecule, but those are general trends. For group, in this case, group 5, nitrogen, phosphorus, 3 plus. And carbon and silicium will have 4 valence electrons. I will see that those can actually play both sides. Very important. Now, you know, those are general trends. That doesn't mean that they have always those value. Most of the time, those elements will work like that. Lithium will have an oxidation state of +1, and fluorine will have an oxidation state of -1. Oxygen, by definition, is also an oxidation state of -2. Hydrogen, for example. Hydrogen is supposed to be in group 1, so it's supposed to be H+. But it could also be in here with fluorine, because it could be theoretically in group 7, because if you're just adding one electron, you have a full octet. Remember, hydrogen doesn't have a full octet of 8, but 2. So theoretically, it could actually grab electron and reduce the compounds. And this is, for example, the case in a substance called, if we take an example of lithium hydride. Very rare elements, but lithium hydride is LEH. This is the lithium here, and the H. And the lithium is less electronegative than hydrogen, meaning hydrogen have more affinity and will grab this electron. In this case, lithium will be a plus 1, and hydrogen will be minus 1. So it's always very important to look at the various components in a molecule to calculate, to see what would be the oxidation state or oxidation number of an element, and see what element is more electronegative in a substance.